And okay, so we had this, commutative square. So it says if we have V and W, which are vector spaces, and we impose both, we place a basis on both of them. So we put a basis B on V and a basis D on W, and we have a linear transformation between them. So we have these coordinate maps, CB and CD. These are the vertical arrows, the ones that are pointing downwards here. And we know that these are isomorphisms. So what we want to be able to do is to rewrite our linear transformation T as a linear transformation from Rn to Rm, right? And so last time we talked about how we could do that. And we came up with this thing in the bottom right-hand corner here, which is this idea that the corresponding linear transformation should be this thing. And if you think about what this thing is doing, it makes sense, right? It says, okay, so I'm going to start with an element in Rn, and I'm going to reverse the coordinate transformation to figure out what the element in V is. And then I'm going to apply the linear transformation, and then I'm going to decode that information by using the coordinate transformation to figure out what it is in Rm. And so that's what this is, right? It's the composition of these three functions, and it does that. So, okay, I think that hopefully makes a lot of sense. So now we know something, right? So we know that linear transformations from Rn to Rm are given by matrices, right? They're in bijective correspondence with matrices, are given by M by N matrices, right? Which, we haven't had much occasion to use this notation because usually we talk about square matrices, but there you go, right? That's the set of all M by N matrices. And so what this means is once I have this linear transformation T hat here, I might be interested in figuring out the corresponding matrix that goes with it. So this gives us a function we're going to call it mdb. Okay, so again, you have to have already kind of specified the basis here in order to be able to define this function. Maybe let me use a different color here. mdb, which takes in a linear transformation from V to W and outputs an M by N matrix, like so. Okay, so what I'm saying by this is what this function does is it says, oh, if you give me a linear transformation T, MBDT, that's a mouthful, MBDT is the matrix representing CD compose T compose C B inverse. Okay, so you can see this is a fairly abstract thing. It doesn't have sort of this nice, at least written the way it currently is written, it doesn't have this nice algorithm for how you would actually compute this in terms of T. Now, luckily in the notes, we can do some manipulation and we can figure out what exactly this thing should look like. And you can check pretty easily that this works out to be the following. So you get mgb of T, and you can calculate its columns by computing the coordinate transformation of T acting on the first basis vector of B, and then the second column is the same sort of thing, but now you act on the second coordinate the second basis vector, and so on and so forth, right? CD, T, B, N, like that. Okay, so you can see both bases coming into play here, right? So here is obviously, here's where the basis D comes into play. And here's where the basis B comes into play. Okay, so from this, you can sort everything out. This is not a hard computational problem. It's often just a long computational problem, right? And again, this is like I've been saying, this is the sort of thing you definitely want to be comfortable with a matrix solver in order to be able to do. And you will be fine to use these on tests and assignments because this does end up being quite a fair amount of work. All right, so let's do, let me just give myself some more space here. Let's do an example here. And the great thing is you can just basically make these examples up yourself, choose your favorite vector spaces, give them an arbitrary basis, choose an arbitrary linear transformation, and just start computing, right? And then find someone else in the class and be like, hey, you do the same exercise and see if your answers match. If your answers match, you probably got it right. And if they don't match, well, then you can go through and you can work with your friend and you can figure out the right answer, okay? So I think that that's kind of a good thing to do. By the way, I think that's just a generally good thing to do, just to kind of go on a side tangent, is a lot of things that students never think about is how you reverse engineer a problem. That's something you don't tend to think about until you get to be, a professor or an instructor. Like, for example, how do I make let's think about 223. If I want you to find the eigenvalues of a matrix, how do I make that matrix, right, that has nice eigenvalues? So if you've never thought about reverse engineering that problem, it's a good exercise because, again, it really cements your foundation in what it is that you're doing. So that's number one. But number two, this idea of like creating questions, I think a lot of people just tend to do the questions that they're given. So the exercise questions, the questions at the end of the book, and few people ever create their own questions. Oh, absolutely, reverse engineering is harder than solving them, right? So for example, because theoretically you need to know a lot more. So for example, in the eigenvalue example, does anyone know how you actually construct the matrix? Like, you've learned it, you actually know the technique, but the technique is more advanced than actually just solving the eigenvalue and eigenvector. So this is kind of an interesting question to me. Do you guys know how you would actually reverse engineer that problem? So you want a matrix which has these eigenvalues and these eigenvectors. What would you do? Because there's an easy way and there's a hard way, right? No, nobody knows? So you guys remember how to diagonalize, right? So in 223, you would have learned that if you're given a matrix, and if that matrix is diagonalizable, then you can write it as P, D, P inverse, where D is the diagonal of eigenvalues, and then the P's are the eigenvectors, right? So to reverse engineer this problem, all you do is you say, okay, what eigenvalues do I want? And you make this a diagonal matrix. And then you say, okay, what eigenvectors do I want? You make that P, and then you compute P, D, P inverse, and you give the student the resulting matrix. And you can do that well before the students have learned about diagonalization, right? So that's how, for example, we reverse engineer that problem. Even something like thinking about how do you reverse engineer a problem of creating a linear system of equations, right? Like, what we'll do is we'll just write down random coefficients and then choose the thing you want to be the solution, plug it in, and use that to get the constants. And a lot of students are kind of like, oh yeah, wow, obviously you could do that. But the first time you ever do this, it kind of slips your brain that you can do these things. But anyway, so like reverse engineering is generally a hard problem. Now, one thing that I would encourage you to do, though, is to create problems of your own and give them to your friends. And this gets you into not only a test maker's mentality, but to make questions, you have to have a good understanding of what it is that you're talking about. So this idea of making even just a small test, make a 2-question test and give it to your friend, and have your friend make a 2-question test and give it to you, and trade and use that to study. That's a phenomenal study technique for 2 reasons. One is obviously you're solving problems, and 2 is you're practicing test writing, right? So when you solve the test that your friend gives you, actually write it like a test. Don't well, I guess in an online environment you can pretty much do whatever you want anyway, but write it like a test and practice your test writing skills. Okay, so just something to keep in mind there. I think that's a great study technique and would really encourage it. Okay, so back to this course. So again, I really just, when I was making this up, I chose 2 vector spaces and just made up a linear function. Of course, it does have to be linear, but just choose your favorite thing. And I made up some bases and then just computed it, right? Doesn't need to be harder than that. You want to practice it? That's a great way to practice. Okay, so I created this. I just made stuff up. Here are 2 vector spaces. We're very familiar with these vector spaces. And here's a linear transformation. It's really not hard to check that this is linear. So kind of the interesting thing that's going to happen is we're mapping from R4 to R3. And so what it's going to do is it's going to take the off diagonals, add them, and put that in terms of the x, okay? And let's use the following basis. So let's use the bases. All right, so I'm going to choose a non-standard basis for B. And even once you have this, once you have a problem, you can create another problem just by changing the basis, right, in this particular example. So even once you've got a linear transformation, just switch up the basis and redo the problem. And you have this kind of infinite font of examples, right, for M2R. And let's just use the standard basis for P2R. And you'll see why I made that choice. Okay? Because the problem is actually easier. I think you want the hardest part of this problem is going to be computing the CD part, right? So the easier your basis is on the codomain, the easier the problem is, as a general rule. That being said, if you're just using computers, it's not a big deal anyway. Okay, so in order to compute this thing, right, what does the definition say? So it says that we need to compute CD T B1, CD, right? These are going to be the columns of our matrix, CD T B3, and CD T. I hope I left myself enough space to actually do the problems. We need to compute these for entries, right? Okay, so, and as a general, the first part isn't too bad, computing T of B1. So, here, let me try and keep it so that you can see what T does at the top of the screen. So it's going to, the 1, 1 element is the x squared element, the 2, 2 is the constant, and then the sum of the off diagonals is the x term. So this is just actually going to give me, x squared plus 1. And now, depending on the D basis, this part can actually be quite tricky. So I chose D to be the standard monomial basis for the polynomials so that we can just read it off. Like that, right? And then, so let's keep going. So this is going to be x squared. So the constant term is there, so x squared minus 1. Right? And now, again, you got to be careful here. So that's going to be -1, 0, 1, right? Not the other way around, because the way that I've written the D basis, the constant term is first, right? So keep that in mind and just be, a little bit careful about that. All right, B3 is just going to be 2x. That's wonderful. So 0, 2, 0. And then, so here's a nice, cool little thing. So the image of B4 here is actually just the 0 polynomial, right? It's actually in the kernel. So we just get 0, 0, 0 here. All right. So are there any questions about that? Does everyone understand what I did at each of those steps, right? So I computed what the T of each of these basis vectors was, each of the basis vectors in B, and then I applied my coordinate transformation to those in order to figure out what they were. And because I chose an easy coordinate or an easy basis for the polynomials, I could just read it off, right? It was just literally the coefficients of whatever the polynomials were. And that's why I chose a nice basis for that. Otherwise, there'd be a lot more work involved. And you know what? Feel sorry for the poor students who had to do this in a non-remote environment and would have been given, could have been given this question in an in-person test without a calculator. Can you imagine if somebody gave you a non-standard basis in the codomain and you actually had to compute? Yeah, and you actually had to compute all those? Oh, that'd be terrible, right? That's like the entire test. The entire test is just, here is one linear transformation in two bases, compute the whole thing. So yeah, I guess there are benefits to being online, right? Okay, and so we conclude MDB. So it's just going to be the matrix whose columns are these things, right? So 1, 0, 1, -1, 0, 1, 0, 2, 0, 0, 0, 0. Okay. Yeah, I mean, row reduction sucks for sure, let alone this row reduction. And actually, you know what? If you had to do this in person, this is actually might be worth thinking about. If you had to do this in person, there's a way that you can do it in a single row reduction. So you can solve all 4 of these in a single row reduction, but you need to think about how you would do it. and not by like computing the inverse matrix or anything like that. But if I actually gave you these 4 problems with a non-standard basis, how could you solve it with a single row reduction? Which is a trick I think that we don't emphasize enough in 223. Okay, so there it is, and that's how you actually compute one of those matrices. And it's not hard. None of those individual steps is difficult. It's just they're often long and involve a lot of work. Okay, so don't hesitate to use a computer to help you out. And let me see if I can make this thing a little bit bigger. So the kind of one theorem that I think happened at the end, and actually, you know what? I went back and I looked at my proof of this today, and I actually don't like my proof. I think there's a better one. But it does still come down to this commutative diagram that I had drawn. So basically, it says what you want to be true. So there's so much notation here, right? And it's easy, I think, to be bogged down by this and be like, oh, this is just gibberish, and I don't understand what this means. What this is saying, okay, is the usual thing. So we know that, again, if you have a composition of linear transformations of Rn to Rm to Rk sort of thing, then you know that if you represent those with matrices, that corresponds to matrix multiplication, right? So what I want to say here is if we had something like this, Rn to Rm to Rk, and this was T and this was S, right? Then we know, so ST as a map from Rn to Rk has a matrix representation. So ST acting on X is Cx, right? Where C is a K by N matrix. Okay, now, because S and T are both linear transformations, they also have matrix representations, right? So same sort of story. So T equals AX for some A in R M by N, and S of X equals BX, B in M K by M. Okay? And what we know from 223, and the reason why matrix multiplication is defined in this weird way, is that there's a theorem which basically says that C is equal to B times A, right? That if you want to compose these two things, and maybe that's obvious, right? Because the proof here is just proof, S T of X is S, well, T of X is A times X, right? And S of X is B times A times X equals BAX, right? And so that matrix multiplication works out in this way. So that's a theorem, and that's not a crazy theorem, right? That's what matrix multiplication is. It's the composition of those linear transformations. So now look again at the proposition at the top of the screen. This is saying the same sort of thing. It's just it's got these weird kind of funky bases hanging around everywhere. But all this says is that, hey, if I compute the matrix version of ST, then that's the matrix of S times the matrix of T, right? And that's correspondingly more or less the exact same theorem. So that's what this is saying, and I don't want you to like freak out about it. It's just saying, listen, this works the way you would expect it to work, right? It does the thing that you want it to do. So that's all that is a nice little sanity check that is correct, okay? So any questions? So I think I'm actually going to, while you're thinking of a question or writing it up, I think I'm actually going to change the proof that I have in the book for this one. I just don't like it. I realize I must have written something in a slightly weird way because it doesn't quite make sense as written. But have you guys seen this big diagram here? It's a beautiful little diagram. And it really shows you, I think, the power of drawing these diagrams. CB, what was this, CD? TF, RN, RN, RK, this is T, this is S. All right, we'll call this T hat, we'll call this S hat. And then if we just compose these as one, this is ST, and then this is ST hat, like that. And this diagram commutes, so that's the proof for me. Yeah, I mean, there's definitely like, there's subscripts in subscripts, so I think things tend to get a little bit small. So you can see here that what I've done is in this diagram that I've drawn, I haven't called it T sub M sub stuff. And I just kind of put a hat over it instead, and that might make it a little bit easier to just, call it hat. But yeah, so this diagram commutes, and the entire proof is just diagram tracing. Is you just say, oh, look, this diagram has to commute. And so, for example, if I start here and take this long path like this, I should get the same answers if I did this, right? That's what the proof is saying. The proof is just exactly that statement. If you take the bottom arrow, then that's the same thing as going across twice like that. And there's a little bit of stuff to actually do there, because you don't know any properties of the dashed arrows. You only know properties of the straight arrows, but you can nonetheless prove these properties by actually, using this fact that this diagram commutes. So it's actually not too bad. The proof isn't too bad. Okay. So in not usual fashion for me anymore, I think that's going to cover the mini lecture, just because I took this one section and broke it into two halves. So let's start working on exercises. I'm very, very excited about the exercises for this week, or for this 6-2. And I really like them. Okay, so I'm going to give you an opportunity to go download those. And question 1 is, here is a linear map from the degree 2 polynomials to the degree 2 polynomials. Here are 2 different bases on it. Let's compute all the possible things that we could compute. Okay, and you can just grind through them. Again, if you're going to do this, some of these can be done without a calculator. Let me think which ones can be done. A can be done without a calculator, and D can be done without a calculator. B and C, I would use a calculator to do. Okay, so A and D you can do right now if you want, but B and C maybe use Octave or something. Now, exercise 2 I think is a lot of fun. So I would say that 2 should be our first priority. Let's try and work on 2. 2 is obviously a lot more theoretical, but is going to be super useful for next week. Okay, so having a good grasp and understanding of problem 2 will really, really help, because it is more proofy, but we're going to use these properties a whole bunch next week. Okay, and then you shouldn't do 3 until you've done 2, just because 3 really depends on 2. You can do 1 and 2 in any order, but make sure you do 2 before you do 3. Okay, so I'll do our standard thing where I make a single gigantic break room, but of course you don't have to go if you don't want to. And then let's work on that. And please ask me questions, because I don't think, again, you guys might just be the best of the best, which is phenomenal if you are, but I have a strange suspicion that some of these are going to give you trouble, and you should ask.